4 billion years ago, our planet did not look wounded by time. It looked uninhabitable. Earth was a volcanic furnace wrapped in a choking atmosphere of carbon dioxide, methane, and toxic vapor. The young oceans were not blue. They were black-green cauldrons, hot with dissolved metals, lashed by lightning, and bombarded from space by rocks left over from the birth of the solar system. If a human could stand there for even 1 second, lungs would burn, skin would blister, and the sky itself would feel hostile. Yet this hell was not empty. It was waiting. For centuries, we imagined life beginning gently, perhaps in a warm little pond under a calm, prehistoric sun. But the deeper science goes, the more disturbing the picture becomes. The first life may not have begun in comfort at all. It may have emerged in darkness, far below the surface, where sunlight never reached and the ocean floor cracked open like wounds in the planet's skin. There, towering hydrothermal vents spewed superheated water rich in iron, sulfur, and hydrogen, building mineral chimneys that looked like alien cathedrals rising from the abyss. These vents were not merely geological curiosities. They were engines. In a world without oxygen, without plants, without any food chain we would recognize, they created steep chemical gradients. Differences in temperature, acidity, and energy that could drive reactions over and over again. Some scientists now believe those gradients were the first battery of life. Not a lightning strike, not a miracle, a natural machine hidden beneath crushing miles of ocean, patiently turning chemistry into possibility. And this is where the mystery becomes enormous. Life is not just matter. A crystal can grow, a storm can organize, but life stores information, copies itself, adapts, and fights to continue. How does chemistry cross that line? How do simple molecules become something that can preserve a pattern against chaos? This is the question that haunts every origin of life experiment, every deep-sea expedition, every simulation of the ancient Earth. We are not just asking where we came from. We are asking how the universe learned to remember. The evidence is fragmented, ancient, and maddeningly incomplete. The oldest rocks on Earth have been melted, crushed, and recycled by plate tectonics. Much of the first chapter of our planet's story has been erased. But a few clues remain. Carbon signatures buried in rocks older than 3.7 billion years, strange dome-shaped structures called stromatolites, and microscopic textures that suggest biology had already appeared early. If those clues are real, then life did not take billions of years to arrive. It may have emerged as soon as the planet stopped being molten. That possibility changes everything. It suggests that once the conditions were right, life may have been not a freak accident, but an urgent event. Something in the chemistry of the early Earth was trying to happen. The planet cooled, oceans condensed, minerals formed, energy flowed. And somewhere in that violent convergence, the first living system may have assembled itself molecule by molecule, hidden from the sky, invisible, fragile, and revolutionary. But here is the most unsettling thought of all. The first life on Earth may have looked nothing like life as we imagine it. No eyes, no mouth, no movement, no struggle we could see. Only microscopic entities clinging to rocks, feeding on chemistry, multiplying in darkness. And yet inside those primitive cells lay the future shape of everything. Forests, whales, insects, dinosaurs, civilizations, memory, grief, music, and us. So what happened down there in the dark? And what secret mechanism turned a planet into the first living world? To understand how life may have begun, we have to descend into a world more alien than most science fiction. At the bottom of the ancient ocean, where sunlight could not penetrate and pressure was hundreds of times greater than at the surface, hydrothermal vents pumped mineral-rich fluids through fractured rock. These vents did not simply release heat. They created natural compartments of stone filled with microscopic pores, like millions of tiny chambers inside a mineral labyrinth. Some researchers believe these chambers acted as the first laboratories of life, concentrating molecules that would otherwise have drifted uselessly through the sea. Inside these pores, chemistry could become trapped, repeated, and refined. Carbon dioxide dissolved in seawater met hydrogen rising from the Earth's crust. Iron-sulfur minerals lined the walls. Proton gradients formed across thin mineral barriers, creating a difference in electrical potential almost like the voltage inside living cells today. This detail is astonishing because every cell in your body still runs on proton gradients. Long before DNA, Long before proteins, the planet may have been performing a crude version of the same energy trick life uses now. The first cells may not have invented this system. They may have stolen it from the Earth itself, but energy alone is not enough. Life also needs structure and information. It needs something like a boundary, a way to separate inside from outside, and something like a code, a method for preserving useful arrangements. Scientists suspect fatty molecules in the ancient ocean may have formed primitive membranes, little bubbles capable of enclosing reactions. At the same time, other molecules may have begun linking into chains. Among the most important candidates is RNA, a remarkable molecule that can both store information and help catalyze chemical reactions. In modern biology, RNA still plays a central role, as if life never completely forgot its first language. Yet the origin of RNA creates another mystery, because RNA itself is complicated. Building it under early Earth conditions is difficult. So perhaps life began even earlier with simpler chemical systems. Networks of reactions that copied patterns imperfectly before true genes existed. In that scenario, the first living things were not full cells at all. They were transitional entities, half chemistry, half biology, unstable but persistent, evolving without yet understanding that they were alive. This is where the story becomes unsettling. The boundary between non-living matter and life may not have been a sudden leap. It may have been a slow blur. Then came the twist. Some of the strongest evidence suggests the earliest life forms were not feeding on sunlight because sunlight was dangerous. Without an ozone layer, ultraviolet radiation blasted the surface with lethal intensity. Instead, the first organisms may have survived by consuming chemical energy from rocks and vent fluids. In other words, life on Earth may have been born in darkness and only later learned to face the sun. That reverses one of our deepest intuitions. We tend to associate life with warmth, daylight, and green abundance. But the first chapter may have belonged to shadow, pressure, metal, and fire. And there is an even bigger implication. If life emerged wherever water, rock, and chemical disequilibrium met for long enough, then Earth may not be unique at all. Moons like Europa and Enceladus, with hidden oceans beneath icy crusts, suddenly look less like frozen wastelands and more like possible echoes of our beginning. The terrifying animation is no longer just about our past. It becomes a preview of what could be happening elsewhere right now, under alien seas, in silence. But one problem remains. Even if chemistry created the first fragile living systems, early Earth was still violent enough to erase them. Asteroid impacts could boil oceans. Volcanoes could poison entire regions. The planet that gave life birth was also fully capable of wiping it out. So how did that first fragile lineage survive long enough to transform an entire world into a living planet? Against every reasonable expectation, life survived. Not because early Earth became gentle, but because the first organisms were shaped by violence from the very beginning. They lived in cracks, beneath sediments, inside mineral pores, and around deep-sea vents where catastrophe on the surface meant little. When asteroids struck and oceans heaved under fire and steam, these tiny pioneers may have endured in the dark, protected by stone and water. The first survivors on Earth were not powerful. They were adaptable, and that quiet ability to persist would become the most important force in the history of the planet. Over immense stretches of time, those primitive cells multiplied, mutated, and spread. They occupied one chemical niche after another, feeding on hydrogen, sulfur, iron, and methane. The planet became a vast experimental field where trillions of microscopic lives were testing ways to endure. Then came one of the most consequential innovations in the history of existence. Some organisms learned to capture sunlight. Photosynthesis was not merely a new survival strategy. It was a planetary weapon. Little by little, ancient microbes began releasing oxygen as waste, and that waste would eventually rewrite the chemistry of the oceans, the atmosphere, and the future of life itself. At first, oxygen was a disaster. To many early organisms, it was poison. It reacted violently with metals and molecules that had existed for ages in a low-oxygen world. The change triggered what scientists call the Great Oxidation Event, a transformation so profound it can be read in ancient rocks across the globe. Oceans changed color. Iron dissolved in seawater combined with oxygen and rained down in colossal layers on the seafloor, leaving behind banded iron formations that miners still extract today. What looks like silent stone is actually the fossilized record of one of the greatest biological upheavals Earth has ever known. And here is the terrifying truth. Life did not simply adapt to Earth. Life remade Earth. The atmosphere you breathe, the ozone shield that protects the surface, the possibility of large animals, forests, and eventually human beings all trace back to invisible organisms no larger than dust. The first life did not just survive the planet's violence. It transformed a hostile world into a biosphere. Every breath you take is, in a sense, an inheritance from creatures so ancient and strange that they lived before bones, before leaves, before sex, before death had the meaning it has now. This is where the story becomes almost unbearable in scale. From those first chemical survivors came every branch of life ever known. The first predators, the first cells with nuclei, the first multicellular experiments, fish, ferns, reptiles, mammals, primates. Every extinct monster and every newborn child, every fear, every ambition, every empire, every prayer, every work of art. The distance between a hydrothermal vent microbe and a human mind feels infinite. And yet it is a single unbroken chain. We are not separate from that ancient darkness. We are its latest expression. But that realization carries a warning. If life began quickly on a violent planet, then existence may be more fragile and more common than we imagined. Fragile, because everything we are depends on conditions that can change. Common, because the universe may be full of worlds where chemistry waits at the edge of becoming alive. Somewhere beneath alien ice or under skies we have never seen, the first cells may be struggling into existence right now, just as they once did here. The universe may be far less dead than it appears. And so the terrifying animation is not terrifying because it shows monsters. It is terrifying because it shows how thin the line really is between lifeless matter and living destiny. The first life on Earth was small, blind, and silent, but inside it was the future of oceans, forests, memory, love, and extinction. We measure our lives in years, civilizations in centuries, and species in millennia. But life began in darkness, endured through catastrophe, and turned a dead world into a story. And somewhere in every living cell, that first impossible struggle is still happening.